So recall that there's three kinds of inferential statistics that we talk about in this class. There's point estimates, when you use a sample statistic, such as a mean, to estimate a population parameter, such as a population mean. There's those point estimates. There's hypothesis testing, where you have the null hypothesis and you see if your data allows you to reject it. And then there's confidence intervals. That's the third kind of inferential statistic we're going to talk about in this class. And now we're going to talk about confidence intervals. And we're only going to talk about them in this video. It's not going to be something we'll talk about for every inferential test that we do afterwards. But I wanted to have you guys understand them so that you'll know that they can be done with all of those other tests. And they're pretty commonly reported in research articles. And so when you see one in a research article, I want you to know how to be able to understand what those confidence intervals are. Confidence intervals are a range of plausible population parameters, usually population means for us psychologists, a range of plausible population means around a point estimate, and usually in psychology it's a sample mean determined using the logic of sampling distribution. So really what confidence intervals are, conceptually, is you observe a sample mean, and these confidence intervals will tell you the kinds of populations that are likely to produce the sample that you actually observed. So now we're making an inference from our sample up about the population, just to try to figure out what kinds of populations would result in the kind of sample that we actually observed. So it's actually a range, so there'll be a lower and an upper limit for these population means, and the confidence interval includes everything in between. So to illustrate how confidence intervals work, what I'd like to do is use the same scenario that was used when we introduced the z-test. So recall that the null hypothesis in that case was that the height of SUU men is the same as the height of American men. And for that, the American men's height was 70 inches and their standard deviation was 4 inches, right? And so now we can draw the population distribution up here. So this is the population distribution if the null hypothesis is true. That is, this is the population where we're going to get our sample from if the null hypothesis is true. So it's going to look something like this. All right, so 70 inches and 4 inches. Okay. And in this scenario, our sample mean was 71.2, our sample size was 100, and our sample standard deviation was 4.2, although the sample standard deviation doesn't influence our z-test at all. So now that we know the sample size that we have, we can calculate what our sampling distribution will look like. So this is the sampling distribution. Remember, so these are the expected sample means if the null hypothesis is true, right? So the kind of sample means that you get from here, if you take a sample of 100, calculate its sample mean, and you put it down here, and you do that for a separate sample of 100 and another sample, and you do that for all possible samples of 100. You calculate every sample mean from all those samples, and you do a frequency distribution down here, right? That's our sampling distribution, and it's going to have the exact same mean. Its standard deviation is going to be the population standard deviation divided by the square root of the sample size, so that's 4 divided by 100, square root is 10, So 0.4. And of course our sample down here of SUU men had, this is our observed sample. Right. And overall, the logic we're going to have here, right, is we're going to try to figure out if our observed sample with a mean of 71.2, is that the kind of sample mean that you expect due to random sampling from this population. And we're hoping to reject the null hypothesis. We're hoping that our sample is going to be taller than the kind of samples you expect from this population. Right, so when we did that, the next step was to figure out our critical region. Right, so that was the 5% split on both sides, where if any sample is beyond that, we would decide they're so extreme they didn't come from this population, right? And so we had our z critical value up here of 1.96, our z critical value over here of negative 1.96, right? Because that's the z-score that has 5%, well, that's got 2.5% on either side. So together they have 5%. So our z critical was plus or minus 1.96. Our z statistic, right, the z-score of this sample mean on this distribution, take the sample mean minus the population, take the sample mean minus the mean of the distribution, so 71.2 minus 70, 1.2 divided by the standard deviation is 3. Right, so our z statistic indicates that our sample mean is 3 standard deviations over on this distribution. So like 1, 2, 3. So it's like way over here. So this sample is really unlikely to have come from this population. It's beyond our critical value. It's in the critical region. So we decided to reject the null hypothesis. So that was as far as the hypothesis testing inferential statistics was able to get us. It allowed us to decide that the SUU population mean is not the same as the American mean. SUU's population mean is not 70. Confidence intervals allow us to go a little further. What they're going to do is they're going to tell us what kinds of populations would produce the kind of sample that we observed. Right? And so it's going to be an interval, a range of population values up here that produce sampling distributions that are likely to include our observed sample mean. So to calculate these 95% confidence intervals, we're going to go from our observed sample and we're going to go up to try to figure out what kind of populations would produce the kind of sample we observed. And so one big difference here from doing the z-test, where you start at the population and go down, we're going to center the sampling distribution around the observed sample. So now the mean here is going to be 71.2 inches. We're actually going to assume that the sample, that the SUU men's heights has the same standard deviation as American men's heights to keep things simple. And of course, when we're doing this, we're going to keep our sample size at 100 again. So that means our standard error is still 0.4. And basically what we're going to do is we're going to go over just as far as we did when we were doing our z-test. We're still going to have our same critical values. But now what we're going to do is we're going to say, so wherever 1.96 standard deviations is over from this, whatever that height value is up here, we're going to say that is the kind of population that's pretty likely to include our sample. And we're going to do the same over here. And together, this range from that population mean to this one, we're going to say all of the populations that are within that range, those are all the kinds of populations that are likely to produce the sample that we observed, the sample mean we observed of 71.2. And so mathematically, all we need to do is calculate this height value, right? And that'll be up here. We can use that to guess the population value up here, and this height value, and you will use that as the guess up here. So this is the whole interval here, and the mean here is going to be our upper limit of this interval, and our mean over here is going to be our lower limit. right, so let's calculate the upper limit first. Right, so what we need to do is we're going to center this around our sample mean, and in this case we're going for the upper limit, so we're going to add our critical value. Right, remember this is how many standard deviations over on the sampling distribution, and we're going to multiply that. We have to turn this standard deviation back into height, inches, so we're going to multiply that by whatever the standard error is. So that'll take us from almost 2 standard deviations, right? That translates to about 0.8 inches. Okay, so we'll plug in our values. So the sample mean is 71.2. The critical value of interest, the one up high here, is 1.96. So that's how many standard deviations we need to go over. Each standard deviation is 0.4. So we're going to go. We need to go over almost 2 standard deviations, which will be almost 0.8. It's actually 0.784. Okay, and we do our math, and we find that the upper limit is 71.98. So this mu upper equals 71.98. So a population with a standard deviation of 4 and a mean of 71.98 is pretty likely to include the observed sample mean that we've had, and populations with means that are even higher are pretty unlikely. They wouldn't be within the kinds of sample means you'd expect 95% of the time, right? So that's kind of why we're doing what we're doing is called a 95% confidence interval. All right, so now we could calculate that lower boundary. So now we'll calculate the lower limit. So that's going to be our sample mean. We're going to go below, and our critical value down there, which is the number of standard deviations below the mean times whatever the standard deviation is. Now we plug our values in. 71.2 minus 1.96 times 0.4. So this, of course, is the same as it was going above because it's symmetrical. All right, so our lower limit is 70.42 inches. All right, so that's up here. All right, so this is the kind of population at the very bottom that is pretty likely to produce the kind of sample we observed. It's the kind of sample that's observed when you look at all the 95% of the most common kind of sample mean. So more extreme than that, or even less likely to produce this kind of sample mean. So we did a 95% confidence interval, but we could have, for example, done a 99% confidence interval. And if we would have done that, what we would have had to have done is switched our critical values here and pushed them out so that this remaining 1% is on the edge. So it'd be 0.005 here and 0.005 here. So we just would have had more extreme critical values. So that would have gone in here. We'd end up with more extreme limits. And so the way you usually write this would be like in a research article or something like that. If we have the 95% confidence interval, which is what we calculated, so that's what we'll do for this example here. The 95% CI for confidence interval equals, then you'd bracket the lower bound, the lower limit, comma, and then put the upper limit. Right, so when you read this in a paper, what it tells you is that these are the kinds of population means that are really plausible values given the observed sample mean. Right, so you just go from your observed sample and you figure out what kinds of populations are likely to produce that sample mean. So I want to explain confidence intervals one more way that hopefully better explains why we do the math the way that we do. And hopefully it'll also unify your understanding of like the z-test and confidence intervals. So the first idea I want to introduce for this is the I'm going to call it the 95% decision rule. And this is used when you do an inferential test where you set alpha at 0.05, which is 5%, right? This is alpha of 5%. And it's also used if you do a 95% confidence interval. So this decision rule is used for both of these. So that's how they're the same, is this what I'm calling a 95% decision rule. And what I mean by this 95% decision rule is that all sample means within 95% of the sampling distribution, right? I just mean by that the 95% in the middle. So all sample means within this area, we decide they are plausibly from that population. That is the population that produced the sampling distribution where 95% was there. So if we're doing a z-test, right, we know this, and given a sample size, we could calculate what this looks like. And usually for a z-test, in this case, right, we would, with an alpha equals 0.05, we'd have 2.5% on either side that we would get rid of. That would be in the critical region, right? And that's how we got plus and minus 1.96, their critical region, right? And so all sample means within this 95% of the sampling distribution, if our sample mean is within that, then we say, well, geez, it's plausible that our sample is from this population. Therefore, we can't reject the null hypothesis, right? So that's how this 95% decision rule fits in with the z-test, or hypothesis testing more generally. It applies to other example inferential statistics as well. But that's how it applies to the z-test. But the same logic is just what we use for 95% confidence intervals. All right, so now to use the 95% decision rule to explain confidence intervals, right, we have our sample mean, that was 71.2 inches, and we'll stick with a sample size of 100. All right, so now what we're going to do is we're going to figure out what kinds of populations produce sampling distributions where it's plausible our observed sample is from that population. And so there's going to be a whole range of populations that have our sample mean as plausible value. So what we want to do for this confidence interval is find the edgemost populations. So we'll start with the upper, right? And so down here, this is the kind of sampling distribution that this population would produce, right? And we're trying to figure out what is that value, what is the value here. And for the z-test, right, we have these cutoffs where there's 95% within, and that's going to be true here too. Right, so we need to figure out what these cutoffs are, and they'd be 1.96 and negative 1.96 because this is a normal distribution. And we want to figure out, what we want to do is put our sample mean, 71.2, right at the bottom. Right, because this is the kind of population, the one with the highest mean that produces a sampling distribution where our sample is within the plausibility range. Right, so any populations that were higher, our sample would be outside of that 95% decision rule. They would be implausibly from that population. So what's this population that's the biggest possible, right? And to figure that out, we just set our sample mean at the bottom of that range, right? So now we just got to calculate this. So in this case, what we need to do is we need to start with our sample mean, and we need to go up that far? Well, we know, because this way it was negative 1.96, now we need to go up 1.96. And these are standard deviation units, so we need to turn those back into inches. So we have to say how many inches are in each standard deviation. Right now 0.4. And this will tell us the upper, the mean of the upper limit for a confidence interval. So you do this math, and this value turns out to be 71.98. So that's how the upper limit is actually determined. So it's the population where the observed sample mean is right at the lower edge of plausibility, but is still plausible. Right? Any population means higher, our sample mean wouldn't be plausible. Of course, a sample mean that's over a little bit is still plausible, right? And so the next thing we'll do is figure out what population below the observed sample mean has the observed sample mean as the upper limit for its plausible sample mean. So for this, we would also draw our sampling distribution, and now we're going to have our sample mean be at the upper edge of the critical region. Right here, we're trying to figure out what this is, because that's the same as this, and we know this critical value on the top is 1.96. The critical region on the bottom is negative 1.96, but we're only interested in the top here. This is the population whose sampling distribution is the one furthest over where our observed sample mean is still in that 95% plausibility range. Right? And so what we need to figure out is what this score is here. And so we know that we need to go over from 71.2, it's a smaller number. How far? Well, we had to go over 1.96 to get there, so to get back we need to go negative 1.96 standard deviations, and the standard deviations are 0.4. So we need to go over almost 2 standard deviations below 71.2. We need to go below the sample mean almost 2 standard deviations. And you get 70.42 inches. So this lower boundary, this lower limit, is 70.42 inches. So these, of course, produce the same values as they did when we did the math before, because the math is interchangeable. It's harder to think about it, how to do the math this way, although this is really the reason that you do the math the way I showed you earlier. And so what this 95% confidence interval did is it produced a lower bound and an upper bound for population means that are really plausible, given how random sampling works, to have produced the sample that we observed in our research study. So it's a way to go from, it's not a point estimate. So our point estimate of the population mean for SUU students is going to be 71.2. And then our confidence interval, the range of plausible values given sampling, random sampling, would be 70.42 inches and 71.98 inches. So these are the kinds of population means that produce the observed sample that we had in our study. So when we do a z-test, we test the hypothesis that our SUU men have the same height as American men. Right? And so usually what we do is we draw our population distribution up here, given our sample size of 100. We could calculate the sampling distribution, and then what we would do is we'd figure out if the observed sample mean of SUU men 71.2 is a plausible value for a population mean of 70. And if it's not, then we reject the null hypothesis. So we can make that exact same decision without doing a z-test by using 95% confidence intervals. And it's because They're both using this 95% decision rule. Right. So if we're doing a z-test at the population distribution level, it'd be 70. What we would do, so 70 would be something around here. All right, so given a population mean of 70, we'd figure out what kind of sampling distributions we would expect due to random sampling from that population. And given this population standard deviation and the sample size, the standard deviation is down here, 0.4. And because we're doing a z-test and we're having alpha of 0.05, our critical values are going to be plus 1.96 and negative 1.96. Right, so any samples that are more extreme than that, we'd reject the null hypothesis. So you could think of that as 1.96 is the critical, that's the number of standard deviations over that we're going to look at. So any sample means that are greater than 1.96 standard deviations away, we're going to reject the null hypothesis. And so recall our 71.2 was more extreme than 1.96. Actually, it's 3 z-scores over, so the drawing's not perfect here, but it was more extreme, so we rejected the null hypothesis. Now I want to show you how to do the hypothesis test using the 95% confidence intervals. Right, so recall what we did for that is we centered, we used the sample mean as our centering point, and we drew the sampling distributions where for the upper limit, the sampling distribution is the one where the sample mean is just at the bottom of the 95% of samples that are middlemost on that distribution, right? And so that was plus 1.96 and negative 1.96 standard deviations away from the center point, which turned out to be 71.98. And then we did the same for our lower limit, so something like that. And for that, the sample mean was, would be here. So sorry, these distributions are a little bit like not exactly aligned properly, but this is where the sample mean was, and this had the same location as that, and that's how we determined the upper limit to be 70.42 because that was 1.96 standard deviations above the sample mean. All right, and so when we were doing our null hypothesis test before, what we wanted to see is if our sample mean is within 1.96 standard deviations. And we found out that it wasn't. It was actually 3 standard deviations over. Well, when we did our confidence intervals, when we created these two, those are the edges of our confidence intervals, right? Those go right up to here. So those are our sample 1.96 standard deviations that way, and 1.96 standard deviations that way, right? And for our null hypothesis, it was 70, and then you went over 1.96. Either way, right? And so right here, what we've done is we reject the null hypothesis here if our sample mean is within 1.96. And what we did here is we determined how far over 1.96 is, right? So these are actually like interchangeable comparison points. So what we did when we calculated this to be 70.42, that is the edge of the plausible population means that could have produced this sample, because our decision rule is the same. Either direction. So 70 is not a plausible population value for the observed sample mean. Just like going the other direction, a sample mean of 72 is not a plausible value for a population with a mean of 70. So either way, 1.96 or whatever your critical value would be is the same cutoff either direction, and you end up making the same decision whether you're going from your sample mean up 1.96 or your population mean down 1.96. Either way, you end up making the exact same decision every time. So you can use 95% confidence intervals to do z-tests, or you can actually do the z-test the regular way. Either way, you end up with the same decision every time.